If you listened to my talk on free will, you heard me imply several times that the standard syllabus used to teach us physics doesn't cover the application area where free will can be discussed meaningfully. I did not mean to imply, however, that physicists haven't tried to extend physics so that it works there as well. I had to dodge that complication because this remains a relatively obscure frontier of physics. In this talk, a coda to my talk, I'd like to try to convey an idea of what research is going on. First, however, I should acknowledge my limitations and direct you to more authoritative sources. I've got 3 books to suggest. To be honest, I haven't finished any one of them yet myself, but I have found them very informative and fascinating. The first book is by Kevin Mitchell. Mitchell answers the free will question as yes. I highly recommend the book, if only for Mitchell's rapid, thorough, and insightful review of the origin and evolution of intelligent life in the opening of the book. The second book is by Robert Sapolsky, who answers no on the question of free will. Sapolsky claims our life is, quote, determined, unquote, as his title says. The book has much to commend it as a source of knowledge about biology, neurobiology, and behavior. Finally, for those of you who have no caution about jumping into a heavy book, I recommend Stuart Kauffman's work, A World Beyond Physics. This book is the product of Kauffman's work with the Santa Fe Institute studying complex phenomenon. As a matter of historical interest, one of the co-founders of the Santa Fe Institute was Murray Gell-Mann. Yes, the same Gell-Mann of the quark model and the totalitarian principle. Gell-Mann saw the limitations of the physics syllabus and jumped right in to help write the future syllabus. I'll warn you that what makes Kauffman's book impenetrable for most of us is the author's attempt to describe the domain of the living world using mathematics. If Kauffman succeeds, if he convinces us that his mathematical formulae really capture reality and have testable predictive power, that will be a major advance that all physicists will welcome and accept. Along the way, however, Kauffman introduces new words. That is why I am introducing you to Stuart Kauffman at this point. The new words Kauffman coins will help us understand the physics beyond the standard syllabus. Here's a brief taste of what you'll find in Kauffman's work on the physics of complexity. In our imagination, the universe can be infinite. Within an infinite universe, there can be infinite patterns, all possible. Now consider this. The universe is finite, at least the part we see. The amount of matter is finite, and the number of elementary particles is a countable number, not infinite. With a finite physical universe, all the patterns and forms expressed in the physical matter at any time are also countable and infinite. Our imagination may run wild, but our universe has a limit. It is a very big limit, I grant you, but the limit makes a difference. Now look around you. We live on a planet filled with living things. Natural selection puts an indelible signature on creation. Specifically, the living forms are very limited in number because so many of them are copies of the same form. Living things have usurped the potential of the physical universe to hold many random patterns, and instead living things have filled the environment with many copies of themselves. Where the laws of physics would fill the world with countless random patterns, the living world has imposed an order, the result of life and natural selection. I should point out that the last bullet point reminds us that the second law of thermodynamics is an inequality. Entropy can increase or stay the same. Life lowers entropy locally where life is found, but the actual entropy production is large. The entropy of the universe grows. Entropy is being exported into space. So now let me give you some vocabulary from Stuart Kauffman's book, A World Beyond Physics. In the following, remember who's talking. I'm one of those reporters trying to get the story right, but keep in mind reporters have limited sources and deadlines. Be prepared to use your own judgment. Kaufman points out that what happens to living things is contingent on the past. Living things are active processes generating the future under the constraints of what already exists. Of course, their present incorporates evidence of their past, as expressed by genes, signal chemicals, neural connections, and so forth. The future of every organism is contingent on all these historical aspects of the current moment. Where reality really goes in the next moment is to a place Kaufman calls, and I quote, adjacent possible, end quote. That adjacent possible is the realm of the possible as it is limited by the contingency of history. Other authors have explained the same thing by saying that the future is found in canals, in a canalized reality, that as time flows, our reality through channels or canals. Most of the landscape is never visited because getting there is unlikely, whereas the adjacent possible is likely. Because of the vast number of relationships in the patterns, there is no way to predict where exactly the next moment goes in the realm of the adjacent possible. History creates canals in the realm of the possible, where the next moment can go, but we don't know where those canals lead. Kaufman describes this by saying the future is unprestatable. We know the future is compatible with the laws of physics, but we can't state in advance what will happen. Perhaps this explanation will help. Physics discovers mathematical formulae that connect the past, present, and future. That is the way it should work. Suppose we represent the world perfectly with a function f that can map the state of the world now into the state of the world in the next moment. Let's point out that the input to a function, that is, the current state, lies in what mathematicians call the domain of the function, while its output, the next moment in time, lies in what mathematicians call the range. Physicists assume the domain and range are the same, and we know them. Then it seems physical determinism must be an obvious conclusion. However, the counter-argument is that physics never predicted this current moment, nor does it appear to predict the future in matters that concern us. So something is wrong with our picture. What is wrong with the picture, according to Kaufman, is that the range, which is the adjacent possible, grows larger as natural processes happen. The world of patterns is interconnected so that patterns enable future patterns. Named patterns become module for larger patterns. Thus, new patterns appear in the expanding adjacent possible. One example Kaufman likes to use in his TED Talks is the iPhone. At one time, the technical domain contained digital and radio frequency integrated silicon chips. They got pushed together in flip phones. Then there were internet modems, calculators, and even the Palm Pilot. Remember that? In any case, in a back closet somewhere in Corning, New York, was Gorilla Glass, waiting for any kind of application, so it would be worthwhile to manufacture this stuff. Then all those modules from the domain got put together in the iPhone, and suddenly we had a new product category, the smartphone. Years later, we can trace the lineage of a diverse population of smartphones. There's the Apple lineage, the Google lineage, and in the Asian markets, an authentic Asian lineage. These named objects make a new domain for the next range of innovation. For example, the distributed commerce applications for the unbanked in the developing nations. Another example should matter to you, and that is your eye. The lens of your eye is made largely of the protein actin, but actin wasn't invented for eyeballs. Instead, it was invented to build the cytoskeleton of your cells. But this abundant actin protein lying around in our cells meant that it was in the domain of the possible, and life could use it to create a lens for the eye using actin from the range of the adjacent possible. So one flaw in the argument of physical determinism is that it doesn't account for the growth of the range of the adjacent possible. The second flaw with physical determinism is that it assumes that the function f can be computed. That is a frontier question. Let me bring the question closer to home by reminding you of a related question. Here is a thought experiment originally proposed by Clerk Maxwell. Suppose you have a box full of a gas at a uniform temperature, and there is a partition in the middle with a door. We then suppose a daemon process that opens and closes the door. The daemon knows the speed of each particle. If a particle on the left is moving faster than average, the daemon lets it move through the door to the right. Conversely, a particle moving slowly on the right is allowed to move to the left. After a few such exchanges, the right side of the box is hotter than the left. Now all we need to do is run a heat engine between the two sides of the box, and we have solved the energy crisis with a perpetual motion machine of the second kind. Of course, this doesn't work. It takes energy to store and compute information. Running the daemon is very expensive. The bottom line is that you are throwing energy away and producing entropy whenever you create a temperature difference. Now go back to the assertion that it is easy to predict the future. It is not. It would take vast energy. In any practical sense, the future is not determinable by a computation based on the past of the elementary particles. So let's hedge our bets and say this is all a matter of degree. For example, we can compute large-scale aspects of the weather days ahead or behind, but small-scale or long-term weather are out of reach for the weather people. On the other hand, weather reports are really valuable. Not exact, but valuable. That is a clue to how we should understand free will. Agents make sophisticated calculations all the time in the real world. They do it by knowing what other agents are operating and how those agents act when they find a situation. Let's try this out. I'll show you one picture, and some of you will know right away from that one picture what happens in the subsequent picture. Here, someone is obviously going to attempt a field goal with a football. They will kick the ball. Where does the ball go? Physics wants to know the momentum imparted by the kick, the angle of the momentum, and of course the gravitational acceleration and maybe wind direction and speed. That's physics. Natural selection wants to know what replicates and persists in the living world of active processes. Natural selection has favored this picture. The picture gets reprinted and persists. Similar pictures were originally published 37 times over history in newspapers across the nation, and they have been subject of countless reruns over the years. As a result of that, most of you can apply the attribute of identity to the picture. Lucy is on the left, Charlie Brown is on the right. Moreover, you easily predict what comes next. It is not the football that goes flying. Charlie Brown ends up in the air. Now, physicists will complain this is an impossible picture. Where is the delta V that lofts Charlie into the air? But who cares? The picture is about a shared meme in our society. You knew the answer immediately depending on your connection to the zeitgeist. It didn't take a lot of energy for you to figure out the answer to this complicated puzzle. But feel entitled to eat a cookie to reward yourself anyhow. Some physicists, like Stuart Kauffman, are working hard to apply formal mathematics to explain why some things are easy, like the relationship of Lucy and Charlie, and some are hard, like predicting the weather. While we wait for that mathematical certainty, we can be confident that our minds can view the world with its abundant connections, and our mind can draw reasonable boundaries of identity around the closely connected but loosely coupled entities. Via this process of abstraction, our mind makes sense of the world, and of course it makes decisions. However, most physicists are not following Kauffman. That would be a fatal career move. You need a job. You need a laboratory. Here's a tip. Most of current physics is already beyond the physics of Newton and Clerk Maxwell, because current physics deals with condensed matter. Condensed matter follows the laws of quantum mechanics, to be sure, but quantum mechanics tells us very little about what is possible and what might be invented next in our physics laboratories. Because I'm watching a remake of Shogun on Netflix, I'll illustrate this with a man at a forge making a sword blade the old-fashioned way. Long before anyone identified atoms or knew the periodic table, they learned by trial and error that pure iron is soft but shock absorbent. It doesn't hold an edge, unfortunately. However, working carbon into iron makes steel, and steel is hard and takes a good edge. Part of the art of sword making is in keeping a soft center for a blade to absorb the shock of striking, while making the outside hard to hold an edge. Another part of the art is forging the metal to impose internal stresses in the material. Then there is quenching and other techniques. The cumulative knowledge developed over centuries by swordsmiths in Japan produced the unparalleled perfection of the katana blade. In the West, we perfected metal for guns, tanks, and aircraft. Welcome to civilization. However, the point here is that all materials research into condensed matter is beyond the kind of physics that makes firm predictions. Physics can't explain how to make a katana. Moreover, physics do not predict, say, superconductivity or silly putty. Both were discovered. You just experiment with nature and learn what is possible. Ultimately, we all want to understand the world we live in and our role in it. Leaving aside religion, I'll offer you two choices. The clockwork universe of Isaac Newton is full of things moving on predictable paths governed by mechanical laws. With what we know now about biology and neuroscience, we can also imagine that our human lives are governed by predictable circuits in our head, observable inputs from parents and society, and a bunch of brain chemicals. Biology may be more complicated than planetary motion, but many say it is still predictable and determined. On the other side, I offer you what one painter called the Garden of Earthly Delights, depicting life on Earth as flesh has evolved over billions of years and mind has developed over the past few thousands. My main talk described the world of flesh with its insistence that it has free will. In this Coda, I've tried to explain that the clockwork universe was always a fantasy. Our living matter sleeps on a bed of condensed matter, and neither life nor condensed matter are explained by the limited physics underpinning the clockwork universe. But physicists don't give up, and many have freely decided to devote their lives to expanding their reach of physics. I expect in 10 years we will still debate free will, but our knowledge of information and collective phenomena will be much greater. Thank you for listening.